let's go into the problem. Now, I'm going to give first a bit of context about this problem and a few examples so you can get a sense of what kind of issue we're dealing with here. So let's look at a few examples of this problem. Now, in this picture, you see some kind of a penguin, and it's talking about switching from hots to cools. And if you look closely, these are actually cigarettes. And this image is a document of an from some data set. And you might be thinking which category this is. Well, it's talking about switching from something to something. So it would be fair to classify it as an advertisement. And that is correct. So then if we go into these kind of documents, you see that it's talking about something about inter-office memo, some date, to and from, and it would be correct to say that because the text on top says inter-office memo, that this should be a memo, and that is perfectly fine. Now, a third example would be, again, you have to and cc and from. If you read the text closely, then you might be tempted to say this is perhaps a letter or an email, perhaps for some reason, but this is still a memo. So this presents kind of the gist of the problem, that this problem has a few aspects. It has the image aspect and it also has the text aspect. So now let's discuss what I tried to do with my thesis and what the main goals of this work were. The main goal is to create a solution that performs as well as possible on real life data. But then now let's go and go deeper a bit about what does it mean as well as possible. And also it is important to know that real life data can be messy. So it can be, as you see in this picture, a bit rotated, or there could be any translations or any transformations on it. And that can happen, for example, if you scan documents through a printer and these documents would appear like that. Oh, let me just accept someone in the lobby. Now, so this is the main goal of this thesis. And now it's also important to discuss why this problem is relevant. And I would like to discuss that first for Radio SG, because they're the ones who sponsored me and helped me to develop this product for them. And it is something that we want to use to be integrated inside the product itself. Now, the product that Radio SG develops is a website called Viewport AI. And it's a software application that helps factories and all kinds of organizations to organize their documents. So you would like to be able to access the right documents at the right time. For example, if you are a worker in a plant, you would like to get the correct and latest version for a document. And you want to make sure that you're following the latest procedures as well. So in Viewport, we have many different documents and categories. And as you might imagine, this means that if the user receives a PDF document, he has to know what is on that image and to be able to categorize the content so that the content itself is ordered. Overall, for industry, this problem requires a lot of effort and expert knowledge. And this is applicable in cases where we have many categories and many documents as well, but also where the differences in categories is very intricate. And you saw that in the memo example. In this case, we saw that these two documents are from the same category, but they have different structure. So we see that on the top part, one of them has a memo text. Now, we looked at two different data sets, and I'm going to explain a bit about them and why they're relevant for this case. So the first data set, I like to call it the tobacco data set. And let's discuss a bit about that data set. It is part of a bigger data set, which is procedures against big tobacco companies. So they were trying to advertise cigarettes in a way that was not allowed, or I'm not particularly interested in what the law case was, but they are a good set of documents, and they're approximately 3,500 and are spread across 10 categories. Now, we also collected an internal data set, which was within Viewport, and this data set is private, so I'm not allowed to show you parts of that data set, but I do want to tell you that it has 15,000 samples across 66 categories. And this is an image from the tobacco data set. Now, just so you can get a sense of what kind of documents we also have. Now, when we're talking about the internal data set, we have far different kind of structure. In this case, you see some kind of a house or a building diagram, and there are many different small texts and different geometric figures. So really a solution that we develop, it has to work for any kind of image. Now, let's talk a bit about what kind of solution we are proposing here. Now, the main idea is that we have models which learn features of documents, and then we learn how to combine the learned features from the text model and then the learned features from the image model. So let's look at the text model first. Now, the main goal of the text model is to classify text into the correct category. That is what it's meant to do. But there's a problem in a sense of that we only have images. So we need to somehow extract the text to be able to make predictions. Now, a solution for that is optical character recognition, which is a technique that allows you to extract text. And it's a software technique. And let's go back to the example from the tobacco dataset. And let's focus in particular in the bottom left corner with the red marked text. Now, if you look closely at this, you might be able to read something, but it is hard for the computer as well to read this kind of text. And from what I see, it says something about Surgeon General's warning. And if we run OCR on this image and we focus on this particular part, we're going to get this result. And as you may notice, these results are not perfect, so they're flawed. But that is still something that we're going to use because we don't have a better alternative to this. And in my perspective, this already is quite good. Now, when it comes to the image model, we're going to pre-process the images, so reduce them in size, do some work on them, and then we're going to run them through an image model. And this model has to predict the correct category from the raw images. Now, we also like to introduce the idea that representations are built from a set of features, and I'm going to go a bit into that. Now, In this image, you see three different levels of abstraction. So from the bottommost level, you see only edges and perhaps circles, while on the second level, you see more and more general features, such as, for example, when we're talking about faces, we see eyes, noses, all kinds of facial features. And on the third level of abstraction, we already start seeing some more face-looking features. So what this image shows is that there are different levels of abstractions when it comes to detecting features and faces. Now, how can we do that? And for that, we decided to use convolutional neural networks. You may have heard about them, but I will just shortly explain what they do. Now, let's go back to the same image that we saw. Well, convolutional neural networks, they learn how to create these filters. So each of these grids, they can be viewed as a filter. And through that, they learn features. So when you learn these features, then you can use them to classify the images. Now, I hope you guys understood what convolutional neural networks are. But if you don't, just don't hesitate to raise your hand and to ask a question if something is not clear. Now, we would like to use these networks in a way that is efficient, because GPU time and also time in general is expensive, GPU time especially. So in this thesis, we worked with a technique called compound scaling. And this technique says that when we scale the depth and the width of the models, we should also scale the resolution with it, with those two. And I will provide a short example about what this means. Now, on this image, we have a very standard artificial neural network with one input layer, one hidden layer, and one output layer. Now, when we're talking about compound scaling, we're talking about depth and width. So a wider network would be scaling it up. A deeper network would be scaling it horizontally. So this is what compound scaling tells us, how to scale the network in a way that is beneficial to the performance of such a network. Now, we would like to use this compound scaling procedure to be able to create better models, but you can only compare models when the comparison is fair. Otherwise, you're just getting unrepresentative results. So let's look how to compare them fairly. Now, imagine that you're trying to compare, you have a data set in which you have 99% of items are tumors. So you're identifying whether a tumor is malignant, and 99% of the tumors are non-malignant in a data set. Well, you might be tempted to create a model that says, well, every time I want to predict that whatever I'm given, whatever kind of image of a tumor I'm given, it was always non-malignant. Well, in this case, you're going to get very high accuracy of your model, but this model will be bad because it will say, okay, I'm 99% accurate, but the 1% that you care about, which are indeed malignant tumors, will be classified as non-malignant because you always classify them as non-malignant. So this is an example of a model that has high accuracy, but is a very bad model. So a solution that we explored in this thesis is to balance the data set in order to compare which model is the best. And I will just give an example now about how we do that. So on the first picture, you see the dataset distribution for the tobacco dataset. And you see that it is quite uneven. Now, to be able to compare them, as I said, fairly, we balance the training set to have equal amount of samples for each category. And this is the distribution on the right. So now we have a way to fairly measure algorithms or methods. Now, when it comes to the comparison that we do, we used the efficient net B3 architecture, which is an architecture that uses compound scaling in the way that I described it. And we compared it to the VGG16 architecture. And this architecture has shown, the VGG16 architecture has shown to be quite well-performing in many of these previous document image recognition tasks. So in this picture, you see that on the validation set, the EfficientNet B3 architecture performed better. And this has translated as well on the test set. So in conclusion, what we did is we taught an image model how to recognize images. We scaled that model alongside the model itself, the depth and the resolution of the model and the image resolution. And this model itself is the EfficientNet architecture, and it performed better than VGG16, which is state-of-art or used in many cases as a high-performing model. Now, the text model learned on text which was extracted through the OCR procedure, which is a procedure which takes the text from an image and tries to reconstruct it as well as possible. And we saw how we can balance the data so that we avoid underrepresentative results. Now, I'm going to go into the next chapter, which is multimodal fusion. But before that, are there any questions? Yeah, Ad has a question.
Yes, I was wondering, Risto, is it really necessary to balance the class distribution if you use quality measures like precision recall and F1 score, as you do actually? So I can understand that for accuracy you would like to balance maybe, but if you use alternative quality measures, is it really necessary?
No, I used accuracy only to do it for so we balanced the data set, and then we only used accuracy as the main measure when it comes for a balanced data set. If we have alternative measures, perhaps, but for me in particular, it's quite hard to understand how well a model is performing if I only look at F1 scores. So for me, accuracy is really a good way to understand, and I think for most people, it is a good way to understand how good a model is. Does that answer your question?
Well, yes, I can understand your preference for accuracy. I just noted that actually in your thesis you also look at alternative quality measures like F1 score.
Yeah, so I look at F1 score for imbalanced data sets because for them, then I know that there's a problem that you cannot measure them in the same way.
Okay, that's clear. Thank you.
Yeah. So any other questions before I continue? Okay, so then I will continue with the next chapter. Now, this chapter is about multimodal fusion, and I know that this may sound daunting, perhaps some futuristic kind of concept, but it is in fact not so difficult once you look into the different parts of it. Now, what we call the modalities of a document are the major dimensions of the problem. And if we look at a document, it is an image itself. It has some kind of a structure of a document. And you can think of this about like the margins between the different paragraphs, any kinds of image features. And it also has the textual features, which are the text and the different features that can arise from text. Now, let's look at unimodal features in particular. And unimodal features would be features which belong to a single modality. And in this case, we're looking at, again, this picture from a few slides before. And we see on the left side, we see a grid of small shapes, perhaps shadows or edges. And these shapes are further built on the top right grid to faces, eyes, noses, etc., etc. And then in the last one, we see that these faces are then used, these noses are then used to identify faces. So these features are called unimodal features, and because they belong to a single modality. Now, a few other examples of this, as I said, number of paragraphs, location of certain paragraphs, perhaps pixel density, as you saw in the advertisement photo, it was quite dense in terms of pixels. As for text, individual words, perhaps count of certain words, it could be also perhaps dates. Okay. Now, let's look at what are bimodal features. And these are features which are unimodal features, unimodal features which are combined in a way to create bimodal features. So for example, if you look at, again, this document from before, you see that you have text, but this text is also located on a part of the document itself. So now this becomes a unimodal feature, text and location on the image. So if you can, if you have that text, you can clearly see that, it is a quite important feature of the overall solution. Now, what is multimodal fusion? Multimodal fusion is a way to map the concepts of one modality into another. So let's take a look in this picture. We have perhaps Michael Jordan playing basketball, who is in the image space, but you also have some text that describes Michael Jordan. And these two things are the same concept because it is still Michael Jordan playing, but the text describes him as a person and the image shows him. So the goal of multimodal fusion is to find this common subspace between the different modalities. And now we're going to look at how this has been done before and how we tried to do it in my thesis. Now, there are two main approaches that are often used in this area of research, and these are the approaches of early fusion and late fusion. And I will now shortly explain what each of those means. Now, if we look at this picture, you have on the left side the early fusion explanation and the right side the late fusion. So let's talk about the early fusion first. In this case, you see that there's an input of an image and an input of a text, which is then transformed into features, or the features of this image are extracted, and then they're merged with the textual features that are extracted into this common blue area here. And then after that, we use a classifier on that whole big block of features. And then from that, we learn the common representation from these two things. Now, when we're talking about late fusion, this has, I like to think, one extra step in the sense of you have the classifier for the image and you have a classifier for text, and then you get the output probabilities for each class. And then you concatenate these output probabilities and you learn from them. So that is the difference between early and late fusion. And we also tried an approach called tensor fusion. And I will explain shortly what this is. So tensor fusion is, in my view, an attempt to fix the shortcomings of early fusion. And that is because in early fusion, the unimodal features tend to be suppressed because the whole representation is built inside this one block directly from the representations that are learned from the text and the image model. So the tensor fusion approach tries to model these unimodal features more explicitly. And I decided not to go very deep into tensor fusion because it will take quite some more time to explain all of the details. So we run experiments on these three different approaches, and what you see on this image are the results from those experiments on the balanced data split, as I explained before. So in that case, we see that the image model achieved an accuracy of 77% and a top 3 accuracy of 94.52%, which means that, so just to clarify what top 3 accuracy means, is how many times, so if you look at a set of samples, how many times it was the correct category was within the top 3 categories predicted by the image model. And this is the same, of course, done for the text model. And we see that the text model had a slightly lower accuracy. Now, when it comes to the fusion approaches, we have, as I said, late fusion, early fusion, and tensor fusion. We also tried to use late fusion with one additional layer, which in theory would make the model have more predictive capacity, because it would have, you would have more, your model would be able to estimate more complex functions, but the results show that this didn't lead to an improvement. So only the single layer late fusion was in the end considered. So we see in this slide that early fusion performed the best with 82% accuracy and a 96% top 3 accuracy. And of course, you have to remember that this is trained only on 80 images per class. So not so many images, and already I think it has 82% accuracy. I think that is quite good. But we will now look into how it performs on a real-life data set which is not balanced. So there you're using really all the information available. So this is also how the training of these 3 different approaches look like. And for late fusion, we just show the late fusion with a single layer, so not the one that I explained, that it had 2 layers and etc. So forget about that one. That one isn't relevant. So even on this graph, you see that early fusion performs best, and tensor fusion tends to have quite hectic performance. And that is because we also saw that tensor fusion is quite difficult to tune. So the parameters themselves were difficult to find in a way that it worked for this data set. Now, how does all of this translate into real life data? So these are really how do you apply this in a real life situation? And perhaps you're given some data set from somewhere and you just directly want to use it. Well, what my idea was initially to train on a balanced set is that perhaps these parameters can generalize across different data sets. And we want to use as much data as possible. So in this case, we use 80% of the data set as training set, and 10% as validation set, and 10% as test set. So we have approximately 13,000, I think, more than 10,000 images for training. And we use the F1 score as the main metric when we're talking about uneven distribution. So why F1 score, perhaps you might ask? Because F1 score accounts for some of these shortcomings that I explained of accuracy. So it would penalize situations where you do not get any of the relevant items correct. So if we go back to the predictor for malignant tumors, if you don't get any of the malignant tumors correct, you would get more and more penalized. So this F1 score is between 0 and 1, and 1 would be the maximum, and 0 would be the absolute worst. And as I explained, top 3 accuracy is whether the correct prediction was within the top 3 predicted categories of the model. How often? Now, what I'm showing you on this slide is the results from the dataset internal that we collected within Radio. And in this case, the relevant items would be the top 3 accuracy, and the F1 score. And the image model achieved 0.885 F1 score, the text model is 0.78, and you can see that early fusion is still the best approach in this case as well. So this perhaps says something about that these parameters for early fusion, late fusion, and tensor fusion, well, tensor fusion not so much, are applicable across data sets. So in this case, I think 95% top 3 accuracy is a pretty good score, and this could be applicable in real life situations. So any questions on this slide? So I hope you guys had enough look into it, so perhaps questions would arise later on, if not now. Okay, so we saw that early fusion performs the best. It performs better than the text and image models, so therefore it is learning from both the text and the image features. And the F1 score increased by 0.03, and the top 3 accuracy is 95.41%. So how can we use this in real life? And this is perhaps something that I always strived in my thesis, that I always do things in ways that can be used in real life. And I do believe that we can use this in a way that we suggest the top 3 categories to the users, and we say, okay, you can use this or this category. And he can decide perhaps what is the best. And we can tell them, okay, you have 95% chance that the category is within those 3 categories. Another option would be to apply the 3 categories without caring that you have 2 extra, perhaps wrong categories. This can be useful, for example, for searching for documents, which is good. And you can also use the top one predictions and accept that there might be some error. Now, what are the implications of this work? Now, I think that using such a small balanced data set to test and to compare methods is a good way to go, because it allows us to experiment fast. And that is very, very important when it comes to machine learning, because GPU time, as I said, is expensive. Early fusion seemed to be the best approach, and we found that tensor fusion is hard to tweak, and the parameters do not generalize well across data sets. So what did we see today? We saw that we can scale convolutional neural networks. We saw how to deal with imbalanced data sets, and we saw some approaches for multimodal fusion. Now, what can be done for the future? We can look to scale the model even further with this compound scaling procedure. This, of course, costs more resources, but it should lead to improvements in accuracy. The deployment is also quite important, because you also need to look at what is the cost to run this model. It can be interesting to look at how tensor fusion can be better tweaked or have a different kind of architecture than the one we explored, so that we can make this work better than perhaps early fusion. And as a last point, weight initializations from another data set can be very useful, because if we go back to the image we saw previously, we can see that these features on the bottommost level are quite general. So they're perhaps edges or shadows, all kinds of small things. Now, an interesting concept is that you can train a network on a very large data set and then use the learned few layers and copy them to your own network. And this has been shown to increase the accuracy of models quite significantly. And this can be perhaps shown for the tobacco data set, that researchers did that for the data set. They trained on a bigger data set, and then they copied some of these weights, and the improvement was more than 10% of accuracy, which is quite significant. Now, this was my presentation. Now you can already raise your hand to ask questions if something is not clear. Thank you.
Thank you, Risto. So let's start with questions from the non-committee members, let's say, so from the audience, so to speak.
Yeah, I think some of them also came a bit late. So if you want to ask something that you didn't understand at all after you came late, then you can tell me. Otherwise, you can watch the presentation as well as a recording later.
So are there any questions from the attendants? Well, if not, then I would suggest that Arno, do you have a question for Risto?
Yes, I do. I always have questions. Can you go back a few slides to where you had this table with the results as your latest, the last table? Yes, this one.
Yeah.
Because we look at all these changes, and I was wondering, are these differences really significant?
Well, when we're talking about the internal data set, so this is something that we only measured over one run. So the reason why I did this whole procedure with balancing the data set and getting results for each of these multimodal fusion methods is because I wanted to understand, well, which is the significantly better method than the other. So I can try to say, okay, I don't want to run this procedure so long for this internal data set, which is large. I want to get the best possible parameters and then just apply it on my data set. So significant for internal, you cannot test that for now. So I haven't done tests on that, but
What you say you cannot test? How do you mean? Does
no,
statistics not apply here?
No. I can test it, of course, but then yeah, at the same time I realized this was already that I had to run these, and yeah, didn't have enough time to do anything more than that.
Right. And the other question I have, you have indeed late and early fusion as being the ones that have been used for a while already.
Yeah.
And then people were not satisfied and thought, well, we should be able to do more fancy, and doing more fancy became tensor fusion.
Yeah, basically, yes.
And what surprises me is that tensor fusion doesn't do very much in your case, although in most cases I wonder whether the differences are significant, statistically speaking. Do you have an explanation why this very new fancy toy in our toolkit actually is not a very good toy?
Yeah, that is a very good question. The reason why I believe this is the case is, even though we looked at a lot of parameters for tensor fusion, and we looked at different ways to create tensor fusion, that because tensor fusion requires 2 hidden layers of this. We also tried it with 1 layer that didn't perform well enough. So it didn't perform, I think, it performed on par with the image model, which was obviously unacceptable. So after tweaking it, it was still quite hectic. So what I believe is that it is overfitting, or the parameters are not quite right. So I do think that there is potential in this approach, but finding parameters for it is difficult, and yeah, I cannot say that it can be better, it can be worse. Yeah, that is just the best that we managed to find.
Now you have to refresh my memory for a moment, because I was thinking that tensor fusion with 1 layer would be the same as early fusion, but it isn't?
No, no, it isn't, because then tensor fusion you would have you have around so every sample it has 10,000 numbers.
Right.
That is quite quite different than early fusion, and where you have each of the modalities is around 100 numbers long. So
yeah, I forgot you get a link from everything to everything. Yes. Yeah. Okay, I'm satisfied. Thank you.
Yeah, thank you.
So in the meantime, are there maybe any questions from the attendants? Okay, then I will continue. So one thing we discussed a lot, Risto, and you also, well, you sort of skipped it during the presentation, is the question, how actually do you define a document in your research?
Yes.
Because my intuition is that a document is a collection of pages, right?
Yes, that is also a good question. I've also had my fair share of wondering, what is a document? And I've looked at through sources, and in fact, there's no exact definition of a document. So A document in this case is only a single page, and this on itself also creates other problems, that you have documents which have many pages. In this case, we take all the documents, all the pages from a PDF document, let's say, and then we just put them in a category. And of course, sometimes you have pages which are not relevant to the to the category itself.
Yeah, so my follow-up question is then maybe, wouldn't it be better to use, let's say, all the relevant pages of a document?
Yes,
so that you can combine the information from multiple pages.
That is a good idea, yes. But there it also becomes then a problem of the resolution and the size of the document. So if you use the whole document as an image, so you look, yeah, it's also, as you see, it's quite difficult to talk about documents. So I mean the PDF document itself. So if you use the PDF document as a whole, as one big image, then when you reduce it to a very small resolution, that causes problem of its own, because then the classifier, in my opinion, would probably have more difficulty in determining. So you would need perhaps a larger resolution, or you would need some kind of a different way to input these images, perhaps a different kind of model for many pages.
Right. So you did not come across any approach in the literature that tries to do something like that?
No, I did not also search for that approach because early in my literature research, I settled on this approach, and I think that simplifies a lot of things. But then again, it's better to have results on the simplified version than to have no results on the complex version.
Right. Yes, I was just wondering if you look at slide 65, if I counted, or sorry.
Is it this one?
Yes. Yeah, that's the one. Yeah.
Okay.
Yeah, I was thinking. So you say you can suggest the top 3?
Yeah.
But I was wondering whether you could maybe use more information from the output of the classifier to say something about, let's say, how likely each of these members of the top 3 are.
Yeah, that's a good question. Now, my Mark, so the supervisor in radio, Mark told me that it is perhaps interesting to consider the category which has the highest probability that is correct the category. I did not include that in this slide because this is something that I haven't looked at, how reliable this is. It could be, I just don't know just yet.
Right, right. Okay, I think I'm satisfied for now. Maybe there are other people who would like to ask a question.
No, I think not.
Apparently not. Okay, then Arno and I will leave this session for a few minutes.
Yeah.
And then we will return after we have determined the grade. We will return and then we will announce the grade immediately. Yeah,
thank you everyone for joining me. For those of you who want to get a full recording of the presentation, they can send me an email or send me a message, and you will receive it shortly.
Yes, okay, so I will be hanging up now and return later.
Yeah. Okay, thank you. And yeah, thank you guys, that was it. Yeah, that's okay then. Yeah, I will do that.